discussed a couple of clustering techniques based on density. Right, we looked at two different approaches to density-based clustering. One is model-based, one is model-free. So in model-based, we fitted kind of a PDF for the data set, and the Gaussian components of the PDF correspond to clusters. In the model-free, there is no such thing as a PDF. We simply estimated the density of the data, right, around various data points. And then we considered high density regions as clusters and low density regions as noise. And then we had some way of identifying the clusters. That is by using so the DB scan is one way of doing that. So now we look at a very different kind of clustering method based on a graph representation of the data set. And even here, ultimately, it will dovetail into some kind of a density-based clustering method. We'll actually come up with a kind of a hybrid of density-based clustering and graph-based clustering, and come up with a very powerful clustering technique. And you'll see how well it can. Because one of the hardest challenges of clustering is to cluster data sets that are non-globular or more randomly shaped or non-convexly shaped clusters. Then you have variability in density and and size. So with all this, how do you do clustering? So that was a challenge. So this clustering technique that we will be talking about in this class has all those properties. So let us see how it works. First of all, let us discuss what is a graph. Right, that is it's a structure which has a bunch of nodes connected or vertices connected by a bunch of edges, right? And the set of edges defines the relationships among the vertices. For example, in this picture, the graph represents a bunch of cities, and most of the edges could represent something like distances, right, between cities, or even routes connecting various cities. Suppose it's some kind of a road network or even a air network. You may not have a direct flight from every city to every city. So wherever there is a flight available, you say there is an edge available. Edge is present, right? Otherwise, edge is absent. So that can give you a graph structure. So in a graph, you have a bunch of vertices or V of G and a bunch of edges E of G. So graph is a combination of the two sets, the vertex set and the edge set. And each edge involves a pair of vertices. It connects into a pair of vertices, and V, the set of all vertices, is a finite non-empty set of vertices. So the edges, right, which is something that connects two vertices, it can be directed or undirected. Like for example, if you look at distance between two cities, in that example, the distance is neutral. There's no direction to it. So that is an undirected edge. But suppose you are looking at a flight route between A and B. It can so happen that there is or at least maybe at a given time or on a given day, there could be a flight going from A to B, but not from B to A. So if your graph represents all possible air routes connecting cities during a certain duration, right, the edges might be directional, they are directed. That is, they might be present from A to B, but not from B to A. Okay, so when there is no such directionality, you say that the graph is undirected, right? So when the edges in the graph have a direction, you call the graph is directed. So that means in principle, between a pair of connected nodes, you can have two edges, one going from A to B, another going from B to A, right? So that is what you have in a directed graph, and it's also called a digraph. Trees, we won't be studying trees in this class, but general tree is a special kind of a graph where there are no loops. Okay. Now, the other terminology in a graph is you have adjacent nodes, that is two nodes which are connected by an edge, and a path, which is a sequence of vertices that connect two nodes in a graph. So if you have a sequence of edges, that is A to B, B to C, C to D, and so on and so forth. So this whole sequence of edges from A to some P, right? That's called a path. Then you have a complete graph, that is a graph in which every vertex is directly connected to every other vertex. It's a fully connected graph. So that is, if you have n nodes, you'll have order n square connections. So here again in a complete graph, if you want to know the number of edges, right, that depends upon what kind of graph it is. Is it directed or undirected? So if it is directed, that means between every pair of nodes. If it's a directed complete graph, then between every pair of nodes you have two edges, one going in on either direction. So since each node is connected to n minus one other nodes, right, and so you have totally n into n minus one edges. That order n square. So there's the number of edges you will have in the graph. So whereas in an undirected graph, a complete undirected graph, if you count it the way you have done before, at n into n minus 1, you can see that each edge is considered twice, right? Going from A to B and B to A, so which is not okay. So you have to divide this number by half, so n into n minus 1 by 2. That's the total number of edges in an undirected graph with n vertices. So here also the number of edges is order n square. Now, so far we talked about graph and edges as if edges are binary, that is, the edges are present or absent. But you can also have a weightage given to the edge, which is what we will do in this class when we discuss how you can use graphs for clustering. So in this example shown on this slide, the weightage is could be distance to the between cities, right? Or you can have that could be represent the cost of the travel between those two cities, cost by air, cost by road, whatever it is. Okay, and so here when you want to write a program, right, involving graphs, usually you will have to have two arrays. One is a 1D array that has a list of all the vertices. Then a 2D array, right, which has what is called an adjacency matrix. It's an n by n matrix where n is the number of vertices. So this matrix can be a binary or it can have graded values. If it is if the weights don't have any special weightage, so then weights are binary. So one is weight is present, zero is absent. Then this adjacency matrix will be a binary matrix. So the ijth element, that is, if A is adjacency matrix, Aij is equal to 1 when, so let us write it down. Okay, so I'll call this A. So Aij is equal to 1 if I and J are connected or they have an edge. Okay, is equal to 0 otherwise. So if there is a weightage on the matrix on the edges, then Aij is equal to that weight value. So here is an example of that. So on the left you have all the nodes, the labels of the nodes. Right. In general, the node may or may not have a label. You can just call them 1, 2, 3, 4. Right. And then you have the adjacency matrix on the right, which tells you what is the distance between cities I and J. Now, what is the connection between graph and data, and how do you cluster data when you represent it as a graph? So this is very simple. If you have, let's say, a bunch of data points, yeah. So if you have a bunch of data points, right? Let's say I have 3 points. Right, and first calculate. So in the graph structure that we will define, the data points will be the nodes, and the edges will be some kind of a similarity between the nodes. Okay, so nodes are data points, and edges is similarity. So then, if you have n points, then you will have order n square connections, right? Your proximity matrix, or you can also call it the similarity matrix. Right, will have n square entries. You can ignore the diagonal entries. If it's undirected, you will have n into n minus 1 by 2. But so that will be a very, we don't need a complete graph in general, because the clusters are not dependent on, when you do clustering, you don't have to consider like point pairs which are very far off from each other. So in the similarity matrix, we don't have to consider entries which are very small, which represent points which are very far from each other. So in order to do that, you apply some kind of a threshold and eliminate all the similarity values which are too small. Okay, so which means so when you have this graph, right? Let us say this distance is too much, A to C is too much, so I'll remove that. Okay, so you end up with only a graph structure defining all the points, where only slightly nearby points are considered and all the far off points are ignored. So once you have a sparse graph like that, you extract what are called connected components in this graph, and these connected components will be the clusters. So how does it work? So you have a bunch of data, right? And you extract some, so that is vectors. From the vectors, you calculate the similarity matrix or the proximity matrix. Then sparsification means apply some threshold. Okay, so that means only when the similarity is greater than some value, I consider that connection. So you might get some graph like this. So now the problem is, so you can actually have a graph here, and it looks like this connection is weak, so I'll chop it out. Maybe these connections are also weak, I chop them, chop them, chop them. So at the end of it, I'll have this graph is divided into three subgraphs. Okay, and each of them is called a connected component. What does it mean? Within the connected component, I can go from any node to any other node. And from between two different connected components, I cannot, there's no path from one node to another. So this idea of a path, you might have noticed is very similar to this density reachability concept, which we encountered in DB scan discussion. It's a very similar idea. So here there is a path between one node to another node within a connected component. There's no path from one node to another node between two connected components. So there's a way of finding it out, and so there's an algorithm for that in graph theory. So I'm not discussing that, but just look at this example. So in this graph, you can see that there are three connected components. So this is one, this is another, this is another. So basically, the logic is, initially you don't have any labels to all the nodes. You start from some node which doesn't have a label. Then let us say I give this label number one, so it is connected component number one. Then I give the same label to all the nodes to which it is connected. Okay, so this gets one, this gets one, this gets one. Now again do the same thing for these fellows. So then the neighbors of this guy should get one, but they already have it. The neighbors of this guy should have one. So this is already one, it has a label. So this doesn't have a label, so this has one. And so on. So now this also will have a label, and so on. So you keep on kind of propagating these labels. Okay, so once you encounter a new node which doesn't have a label, then you update and give it the next label. So you already have a exhausted label number one. So you give this label number two and keep going. So there's an algorithm for that. I'm not going to use it in this course. But this is how you extract the connected components in a graph, and which happen to be the clusters. So that's an interesting idea, an interesting approach to the whole problem of clustering. But that by itself doesn't give you an extra mileage, because there's a more fundamental problem which we have been repeatedly facing, right? In clustering techniques. Now we have seen many clustering techniques. Most of them have this kind of a problem. One problem is so high dimensional data. So when you deal with high dimensional data, if you apply high dimensional, this kind of a graph-based approach to high dimensional data, the similarity will be generally very small when it comes to high dimensional data. So especially if you use a cosine similarity, right? Because when you have many dimensions, the direction is discriminatory enough. You don't need the distance. So that is the idea. So that's why for high dimensional data, like comparing documents, because when you compare documents, you take a very large number of keywords, right? And you extract, you come with some kind of a market basket representation in terms of keywords, and we have done that in your very first, one of the first few classes. So thing is, if you look at cosine similarity based on high dimensional data of documents, So within the document class, a given document class, look at the average percent similarity. So for entertainment class, these are some sample numbers, right? Entertainment class, it is 0.032. Financial, it is 0.03. And so within the class, it is like that. So if you look at across classes, it is something like 0.01. So point is, within the class and across classes, it is not very different. And first of all the proximities are quite low. So if that is the case, then how can you just apply some threshold to proximity and say, right, more than this threshold, it is good. It's same cluster, the both data points are in the same cluster. So that is one point with the high dimensionality. The other point is, again, this is a problem we've been facing quite often, which is the problem with densities or differences in densities or variability in density. So when you apply a fixed threshold and say that everything greater than this, right, is good, it's the same cluster, then you are making an underlying assumption about the density, right? Because the threshold value that you choose has depends on density, and if you choose that value without any knowledge of the density, then it's not going to work. Uh, then the problem with density is it can vary from region to region in the input space, right? So your threshold should also be a variable threshold depending upon the region. Okay, so we haven't done any of that stuff. We have come up with a very simple formulation of data as a graph, and then we applied a simple single threshold. Now, when you have data with multiple densities, where the density is varying from region to region, we have seen this problem, right, in the context of DB scan. So if you have data set like this, A, B are very high density regions. N1 is a background to these two regions. Then you have C and D, which are lower density, but it has higher density than N2 background. Right, in case of DBS, where you choose epsilon and min points, if this density threshold is low enough to find C and D, then all these fellows, so we have drawn this picture, right? Right, density is low enough to capture C and D. Then this is A, this is B, and this is N1. They're all grouped together as one cluster. If the density threshold is high enough to capture A and B as separate clusters, then N1, N2, C, and D, they're all grouped into one cluster. So that's also bad. So you need to somehow come up with a local threshold, right? Your threshold should vary from region to region. So which means you need a concept of not absolute density, but relative density. So within the local current circumstances, what is the density and then what is the density threshold that I have to choose? That your choice of threshold must depend on relative density, not absolute density. But how do you choose this relative density? Okay, so we need to define this a certain kind of similarity which depends on relative density and not on absolute density. So how do we do that? So this density is called, for this we construct what is called a shared nearest neighbor approach. So how does it work? So in a graph, every node has some neighbors. So that is the other nodes to which it is connected. So look at this little graph segment. Look at these two nodes, I and J, which are colored in blue. And I is connected, among others, I is connected to this. It's also connected to these four, this red or brown colored nodes. J is also connected to this, but it's also connected to this, again, the same brown colored nodes. So both of them have lots of nearest neighbors. Among them, there are four who are shared, right? So these four are the shared nearest neighbors. So if two nodes have lots of shared nearest neighbors, then it is like it is understood that they're very close to each other. They are in some sense quite proximal. Okay, so therefore you define the connection strength between these two, or in some sense a proximity or similarity between these two data points in terms of the number of shared nearest neighbors. So the weight connecting this ith node and jth node is now 4, right? And this number 4 has nothing to do with the actual proximity or the actual proximity levels, actual similarity levels. It only depends on this notion of nearest neighbor, right? And therefore, by defining a step like this, we have removed dependence on absolute distances completely. So this step only depends on the nearest neighbors, which is a relative concept. The nearest neighbor, your nearest neighbor could be just your next door guy. Nearest neighbor could be like 10 kilometers away. Right? It depends. If you're in Australia, living in the outback area, your next door guy could be kilometers away, right? Whereas if you are in T Nagar or something, your next door guy could be banging on your wall. So it's a relative concept. The nearest neighbor is a relative concept. By doing that, right, you got rid of the dependence on absolute distances. So this idea of nearest neighbor, right? It's actually we actually encounter it in day-to-day life, right, as a measure of proximity or measure of closeness, right? Can you give me an example of where we use this in real life? Anybody? We do. I mean, a lot of us use it, especially. I mean, students. Younger chaps must be definitely using it. But I don't know if you are able to look at it like that. Okay, I'll give you a clue. Social media.
Is this how social media can recommend friends based on the
Ah,
number of
perfect.
shared connections?
Facebook. Okay, so friend recommendation or friend suggestion, right? So how does it recommend friends? Some X, a new person.
Mutual friends.
Yeah, common friends, mutual friends. That's right. Right. So there it says that certain person has you and that other person has bunch of common friends, mutual friends. So you better connect with that person, right? So the idea is that such people are close to you, okay, proximity. We are doing exactly the same thing here. In fact, this is the kind of ideas that go into those kind of features of Facebook and other social media. So this is the difference between the sparse graph, which we already seen, and this new graph we have defined just now, which is shared nearest neighbor. In a sparse graph, you apply an absolute threshold and cut the graph, and sparsify the graph, right? And whereas in a SNN graph, you only look at the shared nearest neighbors, and then you define this strength between two nodes in terms of number of shared nearest neighbors. So which means if they don't have any shared nearest neighbors, then those two nodes will have zero connection. There's no edge between them. Okay, so with that basis, with a graph like that, there's interesting clustering algorithm which is more powerful than simple sparsity-based graph clustering algorithm. So here, this is called Jarvis or Jarvis Patrick clustering. So here you find out all the k nearest neighbors. For every point you find k nearest neighbor, so which means you have to pick k. That's again a given number. Once you have that, right, and so once you have nearest neighbors, this thing, you can calculate this density, this value, right? Nearest neighbor, shared nearest neighbor strength. What is that? So you first of all you only look at connections. For every node, you have only connections from that node to the its k nearest neighbors. That is first level of sparsification. Then you count the number of shared nearest neighbors, right? And for 2 points, you put them in the same cluster if only if the 2 points share more than t neighbors. First number k simply gives you a sparsification of the network, and then you throw away lots of connections. You throw away all the weak neighbors, far off neighbors. Then between any two nodes will have at least one nearest neighbor, right? And now we want to know, do they have at least t neighbors? So because now this between pairs of nodes, connected nodes, is in terms of number of shared neighbors. Is the number of shared neighbors more than t? Okay, so when you do clustering like this, you get interesting results, but it's a bit brittle in the sense small differences in the threshold can give you very different clustering results, right? So let us look at this example. Look at data set on the left. Okay, the smallest threshold T that does not merge clusters. Here the clusters are this black ellipse and two rectangles in the bottom and all those things. You can see that, right? So you take the minimum threshold at which all these fellows will be separate. Now reduce the threshold a little bit, T minus 1. You see that it is merging this black elliptical annulus with these two rectangles which are so far off. Because what is happening is there is a lot of noise in the background. So this noise ends up connecting all these points with these rectangles which are so far off. Okay, so similarly here, this big look like a flipped question mark, this purple region, right? And this little arc here and this little disc-shaped cluster here, they're all again merged. When you lower the threshold a little bit, there's a lot of mergers going on. So it's slightly brittle, this algorithm. Good thing is it can handle clusters of different sizes, shapes, and densities, just like DBScan. It also works well with high-dimensional data, right? But the problem is it depends on connected components in SNN matrix, and so it is basically brittle. The small changes in threshold can give you very different results. So then this guy said, because here also we are applying an absolute threshold, right, on the connection strength. In this case, the connection strength is the shared nearest neighbor, right, number of shared nearest neighbors. So whereas if you calculate density based on this kind of a graph representation of the shared nearest neighbors, because one good thing about shared nearest neighbors is it got rid of the concept of absolute distances or absolute similarities, which is a great progress. But on that graph, again, you are looking at a single threshold. So whereas if you look at the density of a given point, right, and compute your clusters, will that give you a more robust result? So that was the logic behind this SNN density clustering algorithm. So what they do is they compute the similarity matrix, right? And again, just like before, take only the strongest clusters. So you have this sparse matrix up to step 2. So at this point, if you just apply a threshold and then apply figure out all the clusters, you get this Jarvis Patrick algorithm. Okay, but instead of that, they do something else. They calculate the SNN density of each point. So once you have a graph, how do you find out density from a graph? Right, that is simple. How did you find density in case of DBScan? We said how many other points are located within a distance epsilon, EPS, from a given node, right? That's what we needed, because in the DBScan there's no graph, it's all points and the distances. So how do you find density? From a given point, how many points are there within a radius epsilon? Okay, so we can do exact same thing even with the SNN graph, because because earlier we had similarity or distance, here we had the strength of the edge in the graph. So we use again a similar parameter like epsilon, right, and find the number of points that have SNN similarity of EPS or greater to each point. SNN similarity is basically the distance, the strength of the graph, right, the edge strength, right. Uh, Right. So you just look at all the neighbors, count the number of neighbors with whom you have edge strength of value greater than or equal to epsilon. And that number is considered the SNN density of the point, okay, which is fair enough. Right. Now, once you have a density, just like the DBScan algorithm, you can think of core points, because high density points, right, will simply be called the core points. Okay, that is here we can define the number of min points. If the number of points, the neighbors, right, which are greater than epsilon, uh, which are which have a strength, right, the mutual strength that is greater than epsilon. If that number is greater than min points, then you call it a core point. That data point you call a core point. Right, and if two core points are within a cluster, within a radius epsilon, then they are placed in the same cluster. This is a standard this thing. discard all other points, all the noise points, which are the points, all the non-core points are not within the radius epsilon of a core point. Okay, so all the non-noise, non-core points to clusters depending upon the nearest core point. So this is slightly simplified version than the DBS. So if you do that, the original data set is shown in the panel number A. Right, these are all the points. It's exactly the same, same problem that we saw before. Now you calculate this density, SN density for this data set, right? And so they have looked at the points with high SN density, medium SN density, and low density. So don't even worry about clustering. First, just look at the points that are labeled after the density, right? And if you look at all the high density points, which are the core points, and look at the core points, the core points very nicely capture most of the clusters. Okay, and the medium density points, can you tell me what do the medium density points represent? What are they capturing here? Approximately, what is it? What does it look like?
Border points.
Perfect, very nice. All right, the high density points are like core, which are defined as core points. The medium density point, we didn't define actually a border points in this case. They kind of look like border points. The low density points are obviously noise. Okay, so this is quite robust and handle different densities and sizes and all that. Okay, so you look at this again. So the data set and the colors give you the clusters, right? And it can capture very different kind of very hard kind of cases. But the problem is it doesn't cluster all points, unlike k-means, which clusters all points. And but that might be okay because you want to brand certain points as noise. Okay, and but the main problem is it's computationally quite intensive, because DBscan itself is quite computation intensive, as you will see in the assignment. Right here, you are actually computing first you compute the graph, then you sparsify it, then you find the nearest neighbor, and then find the shared nearest neighbor strength, and you get another graph. Right, then on top of that, you calculate the density and so on and so forth. Okay, so many layers of computation. And because of that, the computation complexity is high, but the results are quite satisfying. Okay, so that is the last method in clustering techniques I want to discuss. Right, and the next topic, again a big topic, we'll be spending pretty much the entire course, remaining part of the course, in the second topic. Okay, that is classification. This also has to do with grouping points into some kind of subsets, but the basis is different, the given data is different. Right, so there are a huge number of techniques for doing that. In fact, a big part of your deep networks, right, can be connected to some kind of classification. So we'll discuss that from next class, but I'll just introduce the concept of classification, and I'll explain how it is different from clustering. So in clustering, what have we done? We have a bunch of So in clustering, we have a bunch of data, x1, x2, and so on, xn. And what is the compulsory information that you have to give to perform clustering? Without that, clustering is undefined. Everything else is extra, but the basic information you have to give in addition to data, what is it that you are supposed to supply? Anybody?
Labels.
No, in clustering there are no labels, and that's one thing that's a distinguishing feature of clustering. There are no labels.
Some measure of similarity.
Perfect. Measure of similarity. Or distance measure. Okay, you need to have one of them and data. That's all. All right. And using this, you need to divide the data set into some groups. What is the criterion? The similarity within the cluster should be high, similarity across clusters should be low. That's all. Right? And we are not even saying how many clusters and all that. You don't have to supply all that. Right? Because in some clustering algorithms, you don't have to supply the number of clusters. Weight by itself gives you something. In some cases like k-means, you have to supply that number. But all that is extra. Right? For it to be called a clustering algorithm, you just have to give the data and the similarity measure. That defines implicitly how to do clustering. Right? Whereas in case of classification, this is where you have to supply the labels. What does that mean? Okay, for every data point X, I need to specify a label, a class label. So that means when I give the data itself, right? So my data X1 or C1, X2, also C1. Okay, so X5 is C2. Right, so I might have K labels, and I have to allocate some label to each of the data points. Right, so given you're given a data like this, then what is the problem of clustering? If you have an unknown point X, what is the label? It has to be one of these labels. So the data given to you is a bunch of data and their corresponding labels, and then you'll be given an unknown point. You have to find out what is that label. So in this case, data is given, similarity measure is given, right? Then you have to tell if you have an unknown point. So where C is a cluster. Okay. So there's a subtle difference but very important difference. So here the labels are something you don't let's not call them labels. The clusters are something that you extract by the algorithm by performing the operation on the data set. It doesn't come with the data. Whereas in classification, the labels come with the data, they're part of the data. Without these labels, the classification problem is undefined. Right? And once you have this data set, each data point along with the label, when you have a new data point, you need to tell what is the label. Like for example, let us take some diagnostics. Okay, so if you have such and such parameters, the person has COVID infection. Right? Some other parameters, there's no COVID infection. So you'll have a bunch of data for which some data correspond to COVID, some data correspond to no COVID. Given this data set, if you have a new person with the same parameters extracted, you need to judge whether the person has COVID or not. Okay, so whereas in case of clustering, you have a bunch of data, some similarity measure, and then see what are the similarity groups within the data set. I mean, there is no question of right labels coming from outside. So these labels coming from outside, right, existence of such labels is a crucial distinguishing feature of classification compared to clustering. But this is the most important thing. So here labels are given. If you think of cluster numbers as labels, right, in clustering, they are generated after clustering. In classification, labels are predefined. Okay. So this is quite an important classification. It's quite an important difference between clustering and classification. Right. We'll look at a bunch of techniques. Now I'll just mention one very simple way of classification. Right. So there are two approaches to classification. One is, okay, can somebody explain what is this very simple way to come up with a classification technique? Because in case of clustering, we start with k-means. What will be a similar approach to classification? What will you at least call it? Or what kind of a clustering technique is k-means clustering? The keyword I'm looking for there. Anybody?
Centroid based.
Ah, very good. So that is prototype based, right? So you have, there's a prototype, there's a representative point for the entire cluster. That's what we did in case of K-means. Similarly, in classification also, you can have a prototype based classification. Okay, what does that mean? So I'll call this point, okay, this is my, I don't know, let's say M1. We'll think of some other notation later. Okay, M2, M3. Now I know that, so that is, this is the representative for class 1, predefined. This is representative for class 2, this is representative for class 3, right? Now, given an, I just have 3 data points. Okay, given this information, if I have a new data point x, right? So this is my x. Okay, what is the class of x? How do you answer this? Simple. Any you assume some information. You think, if I have this information, then I'll do it like this. What would be a reasonable thing to do? Hello, anybody? It's simple, very like really common sense. Compared to your K-means, it's very similar approach. Yeah. Sorry.
Whichever representative X is closest to, it
Ah,
belongs.
so the keywords there is nearest neighbor. Right? So if we apply the nearest neighbor criterion, so then M happens to be the closest one. So the class of M will be given to the 2x. Okay, so then therefore by nearest neighbor criterion, X belongs to class 1. Right? If that is the case, then the entire data set can be, or a data input space can be divided into 3 regions, where each region goes to a certain class. And how do you do that? You just take the perpendicular bisector of this and this and this. Okay, so sorry. So these 3 regions, right? This whole region corresponds to class 1. This whole region corresponds to class 2, and this whole region corresponds to class 3. Okay, and we've already encountered this kind of a partitioning of input space in K-means clustering. What do you call this kind of a partitioning? Man, I'm going to give this in quiz 2, this question. What do you call this kind of partitioning of input space based on nearest neighbor? So if you have a bunch of prototypes, right, you divide the entire input space in terms of nearest neighbor criterion. What do you call it? Voronoi tessellation. Okay, so this is a very simple prototype based method, right? And actually this is a very simple thing, because suppose I give you 100 points along with their labels, right? And but here I'm taking only 3 points. Okay, because let us say I have only 3 classes, but I have 100 data points. I'll give you the data, right? Then how will you take only 3 points? That's not very efficient. You can take more points and come up with a slightly more, probably more accurate classification method. How can you do that? Okay, so think about that. So this basically is a prototype-based classification, which is very similar to K-means. Only thing is the nearest neighbor gives you the label in this fashion. So there's a slightly more improvement beyond this. You can do slightly better job than this. I'll discuss that in the next class. That's tomorrow. But there's another major category of classification techniques called discriminant based classification. So in discriminant based, basically there's a function which is defined for each class, right? And so I'll call this phi1 of x and phi2 of x. There's a function defined, right? And so how do you know a given data point is in class 1 or class 2, right? If I apply the function to the data point, if that evaluation for phi1 is greater than the evaluation for phi2, then x is in class 1, else x is in class 2. So it looks very simple, right? But just under this category, this very broad category of classification techniques, we can bring in like a huge amount of literature from basic discriminant based techniques to linear discriminant analysis and neural networks and deep learning, and like a whole ocean can be of literature can be brought under this one very generic approach to classification, which is called discriminant based classification method. The first one is prototype based method, which is very simple to understand. We just saw like a really preliminary example of that and how to do that. We'll look at a slightly more sophisticated version of that and how to train that and so on, which is very simple, right? But so we'll quickly finish it and move on. Whereas we'll spend a lot of time practically the rest of the course on this second category of methods, which is discriminant based classification method. Okay, so let us pause there. You have any questions now? Hello. Yeah, Sarvesh, you want to say something?
No, I said no questions.
Okay, fine. So have fun and